Well, hello again, and here we go into chapter 25. Yes, I know. What the heck am I doing? I'd like to skip around in the book. I've told you that before. I think chapter 25 on nuclear chemistry fits really nicely after our discussion of the discovery of the nucleus. So that's why I'm doing it. I also think that nuclear chemistry is a hugely important topic that you as educated citizens and future voting citizens of our country need to be aware of. I think you need to know about nuclear power, nuclear waste, and definitely those of you especially that are thinking about a career in medicine need to know about nuclear isotopes and nuclear medicine that's used in the diagnosis and treatment of disease. So this is a picture of Marie Curie. She was born in Poland. She was a Polish citizen. Uh, she was brilliant. She was an amazing researcher, dedicated, tireless, fearless. Um, Her work ultimately caused her death, of course, being exposed to radiation for years and years. It's kind of surprising she lived as long as she did, honestly. She grew up in Poland, went through what we would call high school. Um, However, in Poland, women were not allowed, can you believe it? Not allowed to go to college. So she wanted to travel to a country where she could go to college, and she had to raise money to be able to do that. So she worked as a tutor and a nanny and other things, saving up her money so she could go to France eventually. She actually worked, I believe it was around 8 years after her high school years, and sent her younger sister off to college before herself. Pretty, pretty amazing woman. First Nobel Prize woman won by a woman was her. She discovered an element. She's credited with one on her own and then one with her husband. She shared a Nobel Prize with a couple of guys, her husband, and I can't remember the other one right now, and then also got one of her own. So really brilliant, contemporary of all these guys we've been talking about, all these researchers, and also Einstein. So where did radioactivity kind of get its start? Well, chemists playing around with cathode ray tubes. Wilhelm Röntgen noticed that even though his tube was wrapped in black paper to block the visible light, a phosphorescent screen on the other side of his lab, about 3 meters away, glowed green. And so he realized, since it only did that when the cathode ray tube was on, that something must be coming out of these cathode ray tubes. So here's the two things. Remember, these are the Crookes tubes that I showed the demonstration of. This is the same shape as one that we actually have. And this is a picture of him in the late 1800s. Remember, photographs were around then. We were photographing the Civil War. So it looks kind of weird. It looks a little overexposed, but that is Wilhelm in his laboratory. This is his wife Bertha's hand in Europe. They wear their wedding rings on the right hand, not on the left hand like we do here in the United States. These are her knuckles, what you would call knuckle bones at the end of her palm, and then these are her phalanges, her finger bones. It's said that when she saw this image of herself, seeing the bones inside herself without having to be cut open, that she kind of freaked out and never had another x-ray again. Obviously, this was a big boon for the medical profession, and very, very quickly news spread like wildfire about this new discovery. He named them X-rays because he didn't know what they were, like you do in algebra. X is the unknown. But within a couple of years, it had already made it across the Atlantic and was being used in medicine. So you can probably figure out this cranium has something that shouldn't be there, and that is a bullet. This private, J.G. Jr., was fighting in the Spanish-American War in Cuba and got a bullet in his left occipital lobe. Amazingly, he wasn't paralyzed and he didn't die from it. They put a bandage on him, haired up and healed over, and they sent him out back to the front. I don't know what happened to him afterwards, but Anyhow, crazy stuff. So X-rays were actually the first type of radiation that was discovered. This is a story about his discovery, and you will want to watch this and take a note or two. At the bottom of the note sheet there is a link to this as well, and I'll put it in the classroom assignment. Henri Becquerel was a French chemist, physicist. They kind of were blended at the time. He was looking at fluorescent minerals. There were some interesting minerals. He put them out in the sun, and they bring them back inside into the dark, and they would glow crazy colors. They put some of these in a lot of those Crookes tubes also, the ones that they used to use in shows and demonstrations. Becquerel was working primarily with uranium rocks that contain uranium, and of course uranium is radioactive, but that took a while to figure out. These are kind of like, just, you guys might have had little stick on your ceiling, glow-in-the-dark stars, that kind of thing. So if you put them out in sunlight, they get charged up, and then in the dark they glow. So same kind of thing here. So Becquerel is working with uranium, and he noticed that what they would do typically is not just let them glow in the dark, they would put them on photographic plates. So back in the old days, before digital and before film, they used to take pictures, photographs on glass plates, like window pane glass. They'd coat it with a silver compound and then expose it to light. And they would keep it wrapped up because otherwise it would get exposed. So at any rate, he used to put his uranium salts on photographic film out in the sunlight and then take a look at it afterwards. The story goes that sometime in 1896 he went to do his experiment. It was a cloudy day in Paris, so he stuck his photographic plate and his rock samples in a drawer with a key in between it somehow. I'm not quite sure why that was. But he then looked at the photographic plate after it was not exposed to sun, and this is the image that he saw. So this little part right here is from the key, and you can see the dark area was exposed on the plate, and that came from the uranium salts without sunlight. And this is his handwriting on it right there. Another little interesting fun fact is Marie Curie was a graduate student of Becquerel. So that is what led her into her work on radioactivity. This is Marie and Pierre, her husband, working in their very drafty, huge old shop behind the main physics building. As a woman, she had to go in and out the back doors, and they didn't give her her own laboratory. That was just unheard of. So they worked in a really cold and cavernous building behind the main physics building. Pierre died, unfortunately, in 1906. He stepped out into a street and got hit by a horse and cart, and so that was the end of Pierre. But he was one of her professors. You can see they're not very different in age, a little bit, but she and Pierre worked to discover and filter through tons of uranium ore, and eventually they discovered two elements, as I stated. Marie is the one who coined the term radioactivity, and we now call any kind of rays or particles coming out of a radioactive source, out of the nucleus of a radioactive source, radiation. This gentleman should look familiar from the gold-foiled discovery of the nucleus. He was working with radioactive materials prior to discovering the nucleus. That's why he had the alpha particle emitter in here. He's actually the one that coined the term alpha and beta, so these guys aren't very creative. Rontgen names them X-rays, the unknown, and alpha and beta are the first letters of the Greek alphabet, and needless to say, they stuck. Also, just one little fun fact, Rontgen, his discovery, people wanted to call them Rontgen rays. Obviously, that's a little bit of a mouthful, so we went back to X-rays. So what is Rutherford doing? He's playing around with these alpha and beta particles, and he realizes that they have charges. Of course, they're playing with magnets and electricity as well. And we're going to talk a lot more about these three things. Gamma rays were harder to find, but we'll talk about them as well. So nuclear reactions are very different from chemical reactions. Super important that you understand this. We talked about chemical reactions where the amount of matter at the beginning equals the amount of matter at the end. That is one component of a chemical reaction. The other thing is the atoms are getting more stable because they gain, lose, or share electrons. So either they bond somehow, ionic bond or covalent bond. But all the mass is still present beginning and end. In a nuclear reaction, on the other hand, the unstable atoms are unstable because their nuclei are unstable. And they gain their stability by releasing particles and energy from their nucleus. And the crazy thing is, their mass changes very slightly, but also very measurably. And so you can actually calculate how much energy a nuclear reaction will create if you know the mass change. And of course, the way we know that is from the most famous equation on the planet, E equals mc squared, Albert Einstein's equation, where E is for energy, m is for mass, and c, little c, is for speed of light. Okay, so the speed of light squared times the quantity of matter that's quote-unquote lost. The matter gets converted into energy. And we use this to calculate nuclear power, nuclear bombs, all sorts of nuclear stuff. Inside the nucleus, you know the two particles are protons and neutrons, positive protons and neutral neutrons. And from the nucleus, alpha particles and beta particles and gamma rays can be emitted. So, first one is alpha, and a Greek letter alpha pretty much looks like an A in our alphabet. Beta kind of looks like a capital B with a tail when we write the beta symbol. And then gamma radiation, we symbolize with a little kind of loopy thing. If you visualize in your head what a cursive G looks like, it's kind of like that bottom loop on a cursive G. Alpha, beta, and gamma. These three types of radiation have different characteristics. Alpha particles are positively charged, so they're going to be attracted or bend towards a negatively charged electric field. Beta particles are negatively charged, so they're going to bend towards the positive. And then gamma rays are not matter at all, they're energy, and they are neutral. So what's in an alpha particle? And this is what you can put in that little chart on your note sheet as well, or you can just write it down. Alpha particles are 2 protons and 2 neutrons. And since there's 2 protons, they have a +2 charge. And since a helium atom has a nucleus with 2 protons and 2 neutrons, when we write an alpha particle in decay equations, which we'll be doing later next week, the mass number, 2 plus 2, 4 goes on top. The atomic number, the 2 protons, goes on bottom. Normally you'd stack them right up and down on top of each other, but it doesn't really work that well on my PowerPoint to get them neat and tidy, so forgive me. So in alpha decay, for example, this is a uranium-238 atom's nucleus. Remember, uranium's element 92. It has 92 protons. 238 means it has 100. I can do math on my head. Let's see, 146 neutrons. When something decays, it breaks into pieces. So one thing becomes 2 or more things. So out shoots an alpha particle, and that leaves behind, you can do the math, 238 minus 4, 92 minus 2, thorium 234. Now I don't have to know that it's thorium. I know that element 90 is thorium because I can look on the periodic table. It's down at the bottom on the periodic table. So that's going to be important also in doing equations. So again, 238 becomes thorium. Uranium-238 becomes thorium-234. What the heck? One type of matter turns into an entirely different kind of matter. That's a big deal. In beta decay, something even crazier happens. Okay, in beta decay, a high-speed electron shoots out of the nucleus, and you should go, what? What the heck is going on there, Sketches? there shouldn't be any electrons in the nucleus. You told us there's only neutrons and protons. That's right, except when there isn't. So, carbon-14, we'll talk more about later also, is the radioactive form of carbon. When it undergoes decay, it shoots out a beta particle. So, again, this is our notation. Top is the mass number. Remember, mass number is protons and neutrons. There aren't any protons and neutrons in a beta particle. It's an electron. So, 0. Notice down here, and this gets tricky, negative numbers, it says -1. So what do you have to add to -1 to get 6? You guessed it, it's a 7. That means the carbon-14 turns into nitrogen. The mass number doesn't change. We still have the same number of protons and neutrons, total. But here's the weird thing. In carbon, there's 6 protons and 8 neutrons. In the nitrogen that forms, there are 7 protons and 7 neutrons. So what does that mean? It means a neutron turns into a proton. What the heck? Turns out that's happening every 20 minutes or so in every single atom's nucleus, whether it's radioactive or not. Can you believe it? It's nutters. But they also switch back and forth. It's just that in nuclear decay, instead of the beta particle hitting a proton and making a neutron again, it shoots completely out. It's nutters. All right, gamma rays are just energy, electromagnetic radiation. Gamma radiation is the most energetic, shortest wavelength, worst kind of radiation there is. As far as life forms are concerned, it's what we call ionizing radiation. It knocks electrons off of things, breaks bonds, destroys cells. That's good if you're shooting gamma rays at cancer cells. It's not so good if you get your regular cells shot with it. But that energy comes out and it calms the nucleus down. That's the best thing I can say. It just lowers the energy level and it makes it less unstable, more stable. This is a hilarious little TED Ed. It's very, very cute. You need to watch it on nuclear reactions, so or nuclear, just radiation types. It's at the end also. This is a good explainer as well, and watch that and make comments on that. And then this one is one that you're going to do on Wednesday asynchronously if you haven't done it already, the Ed puzzle for this. And that is where we're going to stop for today. Thanks very much for listening. Have a great rest of your day.